Good morning, everyone, and welcome to Swagelok, Western New York's technical webinar, Regulators Overview. I'm Jeff Namey, Director of Sales and Marketing, and we'd like to thank you for taking the time to join us today. Everyone is currently on mute, but feel free to use the chat function during the presentation to submit questions. At the end of the presentation, we'll offer a time and the opportunity to ask questions as well. On the right side of your screen, you should see a column of screens. You can select the single or double bar above those to reduce them in order to see the full presentation. At Swagelok, Western New York, we're fortunate to have Derrick DiCesare on our staff. As a regional field engineer, Derrick supports our customers across our entire territory through his application expertise and providing evaluation advisory services. His technical knowledge has been recognized by Swagelok Corporation with his recent appointment to Swagelok's newly established Global Pressure and Regulator Subject Matter Expert team. Again, thank you for joining us, and I'm going to turn it over to Derrick so we can get started. Derrick, kick it off.
Thanks, Jeff. So like Jeff said, again, everybody's going to be muted, but please, if you have questions, either type them in or when I'm asking for questions, you're welcome to unmute yourself and let them rip. So as we'll get started here. So like Jeff said, I am a regional field engineer for Swagelok, Western New York. I've been with Western New York for 15 years. My contact information is here as well. So email, phone number. I would appreciate if you didn't call the phone number right now. Other than that, you're welcome to call at any point with technical or otherwise industry-related question. I'd be happy to help you. And always, emails are a great way to get in touch with me. We're going to take a quick look at the agenda through this class. It should be around an hour. It might go a little long, but I understand if you have to run at 12 o'clock. The meeting will go a little bit longer, though, just in the event that there's additional questions or additional content that we get into. So we're going to start with regulator theory and operation. That's going to include regulator basics, different types of regulators, including pressure reducing and back pressure regulators. And then we're going to talk about options with regulators, including but not limited to venting and then sizing. So I hope this is appropriate for everybody. And again, if there are questions, please type them, and we'll be happy to engage with you as they come up. So we're going to talk about some terms real quick, just to get everybody talking the same language. This is a sheet that will be emailed out to everybody after the presentation, just so that you don't get distracted looking through it ahead of time. This is a flow curve, and I hope everybody can see my cursor here in the middle. A flow curve, if you're not familiar with these, are going to chart the regulator flow performance according to outlet pressure, given a certain inlet pressure. So you're going to have your flow on your horizontal axes, you're going to have your outlet pressure on your vertical axes, and then you're going to have this performance line that's going to get charted right through the center there. This portion at the top is going to be your seat load drop or your lockup. The droop is going to be the occurrence of when your line goes from horizontal and starts tapering off. This area on the far side is going to be your choked flow. And your ideal operating range is when this curve is at its most level, its most horizontal. We're going to be talking about these terms some more throughout the presentation. And again, you'll have this reference at the end of the presentation that you can hang on your wall, you can throw it out, you can do whatever you would like, but at least you'll have the information for when you need it. Also, just as a quick overview of our product offering, Swagelok has two different offerings of regulators. We have our analytical and instrumentation regulators, or our K series. These are probably most familiar to some of you that are on this call. They're the green handled regulators. Typically they're 1/4 inch, they can be 1/2 inch. And then we have a process regulator offering, and these are going to be larger. So yes, we have a 1/4 inch offering through there, but they go up to 4 inch in both a pressure reducing and a back pressure style. So we have two different offerings, but they are still pressure regulators, and the whole intention of this is how a pressure reducing and a back pressure regulator function. So just so you're aware of our product offering. So from a very basic standpoint, what is a pressure regulator? It's a mechanical device designed to regulate pressure in response to upstream or downstream system changes. And also to level set, upstream is going to be the inlet side of a regulator. Downstream is going to be the outlet side of a regulator. So upstream, inlet, downstream, outlet. Just so that everybody's clear, not everybody's familiar with that terminology, but I use it a lot in this. So some of the system changes that you can experience can be flow demand in the system. It can be temperature changes. It can be pressure fluctuation, either from your supply pressure or something that happens downstream as well. So if you were to look at this in the system, you've got a pressure reducing on this side. You've got a back pressure regulator on this side of the system. So again, your pressure reducing regulator is going to control pressure by sensing the outlet pressure. So they control their own outlet pressure given an inlet pressure. We're going to see where that sensing element is in a little bit here and how that's going to play with regard to your demand. With a back pressure regulator, they're going to control pressure by sensing the inlet pressure, the upstream side. They control their own upstream pressure. So any changes that happen upstream, they're going to react downstream. So that's how they're basically designed to be used in any process being that generic cylinder in the middle there. But we're going to talk about how they function in a little bit more detail right now. So we're going to start with pressure reducing regulators, as this is going to be the bulk of what we see in industry. Most customers and applications require pressure reducing regulators. Back pressure regulators are a little bit more specialized. So this is a cutaway of our KPR series regulator. This is a single stage pressure reducing regulator. And this is just to get you an idea of some of the internal components. Most single stage regulators are going to look very similar if you were to cut them in half. Of course, when you cut them in half, they don't work anymore, but this is going to give you an idea of all of the internal components from the inlet side to the outlet side. So what I like to do is simplify this, because there's a lot of stuff that, while it's important, ultimately we don't care about when we start talking about the performance. So to simplify that, we're going to break this regulator into two different elements. We're going to have the control element, which is going to be made up of the seat. So the seat is this little rectangular box on either side of this component, which is the Poppet. And then we're going to have our load and sensing element. That's going to be made up of this range spring, as well as a diaphragm. The diaphragm could be a piston, but it has to be some element that's going to be making contact with the system fluid. So to simplify that. So with regard to what these end up seeing, the high pressure side is going to be from this inlet connection to the underside of where the Poppet and seat engage, which means that the other side is going to be the low pressure. So as we compress this spring, that's going to apply force to the top of the Poppet, which is going to force it off the seat and create a pressure drop, establishing our low pressure on the outlet side. So again, otherwise there's no opening. This just, the Poppet and the seat engage and basically create a shut-off scenario. So in order to open it up, we've got to apply pressure on the top through the spring. Whoops. Go back. Sorry about that. Okay. And then your sensing element, whether that's a diaphragm or a piston, that's there to balance the force based on what happens downstream. So we're going to see an animation of this. This is also on our website, so you're going to see this work in not real time, but you're going to see what happens as we adjust our handle. You're going to go from 0 outlet pressure to increasing pressure. And as you back the handle out, you're effectively able to control that outlet pressure and reduce it. Pretty simple. So to go a little bit deeper on how a regulator is going to work, It works on a balance of forces principle. Come on. I got fat fingers today. It keeps hitting that scroll bar here. So F1 is going to be this range spring force. This is going to be the force that the spring applies on the top side of this stop plate into the diaphragm, into the sensing element. F2, as we're going to call it, is going to be the poppet spring force. So this little spring underside of the poppet, that's really to just maintain engagement of the poppet to the seat so that in a resting case, it's trying to maintain a shut-off state. F3 is going to be our outlet pressure force. So this entire volume in here is going to be your outlet pressure acting on the underside of the diaphragm or the piston. And then F4 is going to be the inlet pressure force, and that's going to act on the underside of the poppet. I'm going to move those arrows down, but it acts under here, forcing the poppet up. So if we're looking at the direction of where all those arrows are going, we end up with a balanced equation of F1 being our downward force, having to equal F2 plus F3 plus F4. So that's the equation that regulator and all regulators are trying to achieve under normal operation, is a harmonious balance of forces from the spring force to all of these other inlet, outlet, and the poppet spring force. So we're going to come back to that equation in a little bit just to see if everybody remembers. I'm going to talk real quick about some performance criteria with regard to regulators. So lockup, we talked about this very briefly when I was looking at the initial flow curves. So lockup is going to be the difference between a flowing and non-flowing condition. So what you see here is your flow is running, the valve is open. As we close this valve, the outlet pressure is going to rise. So when we go from a flowing condition, let's say we're at 4 standard cubic feet per minute, as we drop that flow down to 0, you're going to see the flow requirement downstream cause this outlet pressure to rise. So this little range in here is called lockup. So it's not the entire thing, even though that's part of it. But the lockup is going from flowing to non-flowing. That's a huge, as a percentage, a much larger change than from going over here. So we have to be aware of that. In the event that this gauge was a 0 to 30 PSI, and let's say that we're running at 28. As we shut this off, there's a potential that this gauge ends up being pegged. So we've got to make sure that some of our other components are sized appropriately, or there's a consideration to handle that pressure increase. Droop. Droop is going to be the reduction of the outlet pressure as we increase flow. So if we were to set our inlet pressure at 500 PSI, our outlet pressure is at around 15 PSI. As we increase our flow, we're going to see that outlet pressure change. So if we think of what happens as we're constantly increasing the flow through here, we're not allowing the pressure to stay inside of the regulator, which means that the force under here decreases. Ultimately, that's going to cause a decrease in the outlet pressure. This happens with every regulator in the world has droop. It's just how extreme is this curve. Obviously, for these two different conditions, whether it's a 500 PSI inlet or 100 PSI inlet, you have different droop intensities. So depending on your system, one or both may be appropriate, or neither would be appropriate. It all depends what you're trying to do. So why is droop important? And ultimately, when we're sizing a regulator, you know that you have a high pressure that you need to get to a lower pressure. And usually when we're sizing this, when I get a request, it's I need to achieve this outlet pressure at this flow, which is great, except in practice, usually it's not just one flow. You've got to try and hold that pressure the same across a wide range of flows, from a low flow to a high flow, compared to normal. So when we look at that curve, the curve is not necessarily horizontal, so we've got to decide where this gets placed to account for your system demand in here. So again, just to show with numbers, Assuming that we're using this flow curve here, the 500 PSI inlet, and we're going to set the static outlet pressure at 22. We don't set regulators when there's no flow. You're going to see why in a second. As we increase our flow to 2 standard cubic feet per minute, the outlet drops from the 22 that we originally set down to about 16 PSI. So we just lost 6 PSI because we set it in a no flow condition. As we continue to increase the flow to 4 to 6 to 8 standard cubic feet per minute, we see that pressure continue to drop. And that's droop. That's by setting an initial pressure, the regulator is not able to keep up with this same outlet pressure given the flow demand. So that's how droop is going to affect. That's assuming that we don't address the handle, that we don't try and make any adjustment from here to bring it back up to the 22 that we were trying to achieve. So something to be aware of. Every regulator has published flow curves or should have published flow curves regardless of manufacturer. It's just how easy that manufacturer makes it to find them. Choke flow. Choke flow was that shaded area that we talked about earlier in that overview. This is when a regulator is in its full open position. And at that point, it's not regulating pressure. It's acting as a restricting orifice. Another thing to think about with this, that's kind of the CV value that's published is going to relate to this choked flow condition. So when you see this relatively flat line, as soon as that tapers off and goes more vertical than horizontal, that's when you're in choked flow. That's not where you want to size a regulator. At that point, increasing the spring load is not going to increase the pressure, and it's also not going to increase the flow. The regulator is wide open. So we want to avoid this condition. Again, our optimal flow range is the portion where the regulator should operate. This is the best performance, where it's at its flattest, and this is relating to this 500 PSI inlet regulator, not the 100 PSI. So we think about some other effects on our performance of the regulators. We have creep. So creep is going to be the outlet pressure increasing over time while the regulator is supposed to be in an off orientation, which means that the poppet's not fully engaging with the seat. It's not creating a good seal. Typically, this is caused by particulate or debris or infrequently deformation. Usually it's debris from not being properly filtered. If the poppet doesn't seat, that allows the inlet pressure to constantly bleed from the inlet to the outlet, which causes an increase in system pressure downstream, which can cause gas cylinders to fully deplete overnight. It can cause damage downstream. At some point, there has to be some either balance where the inlet and outlet are the same pressure. Your inlet pressure goes to 0, or you fill the room with some other leak or something else downstream happens. So we want to be aware. We want to try and filter out the gas or the liquid before it gets to the regulator, because this seat in here likes to catch anything, especially metals and other dirt particulates. The supply pressure effect, this is also called inlet dependency. There we go. So this is the relationship with outlet pressure versus inlet pressure. So if the inlet pressure drops, the outlet pressure goes up. And likewise, if the inlet pressure goes up, the outlet pressure drops. So it's an inverse relationship with a single stage regulator. And that's going to go back to our balance of force equation. If we think of F1 equals F2 plus F3 plus F4. In this situation, we do not change F1. We do not change F2. Those are constants. So if F1 and F2 are the same, if we increase F3, F4 has to go down. In order to keep that equation balanced, that has to happen. Likewise, if it's the other way. So we're going to show this in relation to a standard gas cylinder. In this case, our cylinder is at 3,600 PSI. We're trying to control an outlet of 50 PSI. And right now we're flowing through and everything is great. over time, our cylinder is going to deplete. We're going to start losing cylinder pressure. So in this case, we've lost 1,000 PSI. Without adjusting this handle, our outlet pressure has increased 10 PSI. So we saw a 1% effect of the difference between our inlet pressure to the outlet pressure. We lost 100, or we lost 1,000 rather, which means that we gained 10 PSI downstream. So as we continue to deplete this cylinder, at 3,000 PSI, that cylinder is pretty much empty and ready to be swapped out. Our outlet pressure went from 50 to 80 PSI. So hopefully the gauge is sized appropriately. We don't have a 0 to 60 because at that point it would be decoration, but also downstream of that, we need to be aware of what can happen if we don't address this up front. So the supply pressure effects for Swagelok regulators are all listed in the catalog overview page. So this is a cut sheet of the KPR. This is the top snippet of it. So depending on the flow coefficient that you choose and the control range that are selected, this is going to be the resulting supply pressure effects that you can expect through that regulator. So the 1% that we were looking at was a 0 to 100 control with a 0.06 flow coefficient. So the supply pressure effect, it may not be called that from other manufacturers. From Swagelok, it will be called that, and that's where to find it for each of the regulator series in our K series line. So to combat the effects of supply pressure effects, there is a two-stage regulator or a cylinder regulator. So for Swagelok, that's the KCY. So instead of doing a single-stage pressure reduction, this does a two-stage pressure reduction. And we're going to show you how that works right here. This is how it's set up. So your inlet, your first stage is actually this lower one. There's an anti-tamper nut here so that it's preset. It's done at the factory. As you buy one of these, you don't have to monkey with this at all. It just stays with a set outlet pressure, which never sees the atmosphere afterwards. It's being set ahead of time at 500 PSI, and then it's directly fed into the second stage, and that's the one that we can affect what the outlet pressure is. So again, a little bit of how this works. Your inlet pressure goes in, it goes through a first stage pressure reduction that's internally ported into the second stage. If you buy one of these, you'll see a little port in here that's got a hex plug. That's just to drill this hole into there, into the inlet of the second stage. And then it goes to the outlet. So there's some other notes in here about how the supply pressure effects works, but we're going to talk about that instead right here. So the two-stage regulator is being shown as two different single-stage regulators just to show what the effect happens on this middle stage and the outlet pressure. So same scenario, you've got a 3,600 PSI cylinder, you're trying to control it to 50 PSI. As the cylinder depletes, what would have been a 10 PSI increase in pressure to the outlet now is a 10 PSI increase to the second regulator. So since the inlet pressure went up technically, you see a decrease in system pressure. So if this is 1% and this one is 1%, the ultimate effect of this 1,000 PSI change is 0.1 PSI, so it's 0.01% of your inlet pressure change that's being extended to the actual system. So in the same scenario, we've lost 3,000 PSI in the inlet. The cylinder's nearly depleted. The effect that that has downstream on our system is 0.3 PSI. And it's a decrease, so we don't have to worry about seeing a surge in pressure downstream that can affect mass flow controllers, gauges, transmitters, GCs, anything else. So I'm going to stop for a minute, see if anybody has any questions. I know we're going kind of fast through this, but just want to check where everybody is. See if I can get to the chat. So There's a question here, how to use the Swagelok CV calculator. Okay, we'll go into that. So the CV calculator, so everybody's aware, on swagelok.com, under the toolbox, there are a number of resources that Swagelok Corporate has allowed us to have and use. So there's a couple of things in here. There's a CV calculator. There's also a flow curve generator. But with regard to the CV calculator, the one thing I want to draw your attention to is it's for valves. It's not for regulators. So if we are going to size for flow for a regulator, ultimately we don't want to use the CV calculator. We want to use the regulator flow curve generator instead. But in general, in how you would use the CV calculator, you're either going to calculate for flow coefficient or for flow, depending on which one of these two pieces of data you have and you know. You're going to decide if it's a liquid or a gas. You're going to do your inlet versus outlet pressure. You get to choose your units as well, whether it's PSI, whether it's bar, etc. You input a temperature, you select your medium. If you don't see your media here, but you do know what the specific gravity is, you can overwrite it. And then by typing in, let's just say it's 100 psig, going to 85 psig inside. So we're going to do a flow calculation just to see what we can get through here. And our flow coefficient we're going to say is 0.43. And I want to know the flow of the gas in, it doesn't matter. Oh, it's a liquid calculation. Flow of the liquid in gallons per minute. As we hit this, the maximum flow we can expect in this situation with this flow coefficient, excuse me, is going to be 1.4 gallons per minute. So the other resource is going to be the regulator flow curve generator. So this goes through kind of the background of it, but I'll show you how to use this real quick. As we click on this, excuse me, this is going to allow us to create a flow curve for up to 4 different regulators. Unfortunately, this is limited to the RHPS series, the process regulators, and not the K series. But it's going to be basically the same kind of thing with a pressure reducing. You get to pick what units you want to work with. So PSIG, cubic feet per minute. This is also just for gas. It's not for liquids. And then from here, you're going to drop down to each of the different regulator series. So if we have one in mind, so in RSH4, that's a 1/2-inch regulator. We're going to do a low outlet pressure. The gas we'll assume is going to be air. The inlet pressure we'll say is 1500 psi, and the set pressure is going to be 25 psig inside. After we put in all of our system conditions, when we hit calculate, it's going to create a flow curve based on our working parameters. So this is going to assume, and we can look at the summary of this, it's going to take our inlet condition, it's going to take our outlet set point, it's going to take our gas into effect, and it's going to chart what the resulting flow curve will be for this regulator. You're going to see 2 lines. You're going to see the actual flow curve itself, and you're going to see this other color line. It could be yellow, could be gold, could be how your eyes pick this up. This is going to be your line velocity, your line velocity line. So what we want to do is make sure that it's appropriate on the left side of that line velocity. If you're to the right of that, you're really exceeding what the recommended line velocity is for that gas. At that point, you could see excessive noise, you could see a lot of vibration, and potential damage downstream to other components. So we want to try and pick something to the left of this line velocity line. This is going to be extended from, you could draw this all the way down and all the way up. It's going to be based on the gas, it's going to be based on the orifice of the regulator. So when we're sizing a regulator, we don't want to use the flow coefficient calculator. We want to use the flow curve generator. I hope that answers your question. Any other questions? Okay. The Joule-Thompson effect. This happens with every gas. Basically, it's going to be a temperature change by taking a high pressure, turning it into a low pressure. Typically, it's going to be a negative effect. So it's going to take a gas or take a liquid, it's going to cool it. So in this example, natural gas, there's going to be a temperature change of 1 degree Celsius for every 2 bar drop in pressure, or 30 psi, however your units work. So we want to know about that, because if you're going to do a huge pressure drop, you're going to have a significant temperature change, which can cause icing of the line. So your inlet is on this side here. So you're seeing a little condensation build up. It gets so cold downstream that you actually start icing up on the outside of the tubing or the pipe or whatever the system is run in. Just based on that temperature change, it's picking up moisture in the atmosphere and freezing to the outside, the outlet of the regulator of the system. You can even see the inlet side back here, which will show in a better picture a couple slides from now. The inlet to the pilot regulator is not iced up either. So it's, as that pressure drops significantly, you can see icing on the outlet side. Oops. So to compensate for that, we can either heat the gas before it goes in. We really don't want to heat it afterwards. You can, but we want to make sure it's warm enough on the inlet side, or use a 2-stage pressure drop. And instead of doing a single pressure drop with that huge pressure change that then creates that large temperature differential, you drop it in 2 stages or 3, or is dependent on the gas, depending on the situation, how many additional pressure drops we need to do. There are a couple of gases that actually warm up. It's hydrogen, helium, and neon, in case you're on Jeopardy and that question comes up. Like we talked about, the flow coefficient of a regulator is measured when the regulator is wide open. So it's good to know, but we don't want to size based on that, because if you are, then you're not using it as a regulator. We're using it as a flow control orifice. So it's good for just a quick look. You know, if you're using the calculator and you say, hey, I need a flow coefficient of 0.2, you know that your regulator should be at least 0.2 in most cases. But really the best thing we want to look at to make sure we can get the flow is to look at published flow curves, or to use the flow curve generator. Real quick, another resource I want to point you to in here, as we're kind of jumping back and forth. Within, where was it? In our catalogs, we publish a lot of the flow curves, but we don't publish all of them. In these catalogs, we have a standalone resource that is just a flow curve database. So within our electronic desktop reference, you can look at this online as well. It's available online, but pressure regulator flow curve tech bulletin. So this is 216 pages dedicated to just tested flow curves for both series, both the K series and the RHPS. There are gas, there are liquid. There are, the first couple of pages tell you how to convert from what the flow is, what the media is drawn as. So it's either nitrogen or it's a light oil. Usually you're not running one of those two. So it shows you how to correct the flow curves based on the media that you're running, or how to come up with that correction in the event it's not listed on that chart. So this is a great reference when we are trying to size based on flow. We're going to have the supply pressure effect called out in here. We're going to have the control range, and there's going to be a lot of detail in here for making sure that these are appropriate. And real quick, I was playing with this before. So if you go to our webpage, off of Swagelok.com, if you go to the Swagelok Western New York webpage, which means that you would be registered for it, there's a couple of things in here. Under the Resources tab, we have that electronic desktop technical reference for download right here. It used to come on a little flash drive. We've kind of updated based on COVID to be able to just download it right from our website. In addition to that, if you click on Regulator Resources, this is where you're going to find your flow curve generator, as well as that tech bulletin, which is going to reference us back to the Swagelok.com. But all this is online. It should be fairly easy to get to. There's a lot of resources available, so I encourage you to take advantage of those, especially the EDTR. That's a great tool that I use every day. All right. So back to regulators. Don't size them off of flow coefficient. Use flow curves or other software to make sure that these are appropriate. The CV is important, but that's not how you size them. The way that we do use them in industry is typically to size relief valves, because if a regulator is to fail, it's going to fail in an open orientation. There's very few ways that a regulator fails closed. Typically, it fails open. And if it does fail open, you want to know what the maximum flow you can get through there is, so that if you are sizing a relief valve, you know how much volume you have to relieve from the system. All right, any questions on pressure reducing regulators? All right. Then we're going to get into back pressure regulators. Like we talked about earlier, these are designed to control the upstream pressure. So as we saw with the pressure reducing, it's controlling everything on the outlet of the regulator. The back pressure regulator works backwards to that. It's trying to control the upstreams, trying to control the inlet side. So when we look at the cutaway of a back pressure regulator, it's going to look pretty similar. This one does not have a poppet. Some of the higher pressure ones do, just to maintain a good seal on there. But in this case, for a single back pressure regulator, this one does not have a poppet. Manuel, we're going to talk about pilot regulators in a little bit, but in general, yes, your pilot regulator is a single stage pressure reducing regulator, and it will operate similarly. And yes, when we talk about preheating and gas, there are some factors. You want to know your environment. You want to know what the gas is. You want to know what the heat is that you can apply to it. Ultimately, you want to know your phase curve of the gas to know how high it should be, so that you're not causing a phase change in the gas. And you want to make sure that the seals in the system, whether it's a regulator, whether it's a gauge or a ball valve, a needle valve, et cetera, that you don't overheat it and cause an issue with some other components. But the main one is the process temperature, the external temperature, the environment, the gas, and then what power you have, whether it's going to be electrically traced or steam traced. Okay, back pressure regulator. So again, it's very similar. It's backwards of the single stage regulator, and you're going to see a lot of similar components. This one doesn't have a poppet. When we get into the higher pressure ones, we do put a poppet in there just to make sure that we do get relative sealing under normal operation. You see a lot of additional components just based on the complexity of how this poppet assembly has to work. But your theory is going to be pretty similar. You're going to set your outlet pressure, or your inlet pressure rather. So as this increases, you're applying a force to the top side of the seat. The seat in this case is an O-ring, so it's an O-ring and diaphragm. When you do that, the seat is closed. You're not getting flow through there. So as long as the inlet pressure is less than what your set point is, you have no flow through there. What we care about is if your inlet pressure exceeds that set point, then it's going to vent through your outlet. So it acts very similar to a relief valve. And that's the intention, is that you have a very sensitive sensing element because of the size, that it's able to sense changes in your upstream pressure better than a relief valve. There are some limitations. Relief valves are great, especially in higher pressures because of the small sensing element, but at low pressures, the back pressure regulator is the way to go to maintain a set inlet pressure. So we're going to see this in practice. Excuse me. we go. So we're applying a pressure to the spring. So right now we're closed off. You're going to see our inlet pressure start to build. And as soon as it hits that cracking pressure, you're going to see the excess vent to the outlet until the system is exhausted enough that it comes back to the set point that we're trying to achieve. Again, very similar to a relief valve. We still have a balance of forces equation for a back pressure regulator. It's a little bit simpler. You still have F1 as the spring force. F2 is going to be your inlet pressure force instead of the Poppet spring force, because there's no Poppet spring in this instance. And then F3 is going to be your outlet pressure force. Most back pressure regulators just go to atmosphere because we don't want this in the system, or it goes back to some recycling loop to reuse the sample if it's a liquid, or back to a pump to regenerate it back into the system for gases, depending on the gas, depending on a lot of things. When it's present, this has to be lower than the inlet pressure, because if it's not, there's a chance that this opens up and you actually backfill into the system. There's no check valve built into this, so the outlet has to be at a lower pressure than the inlet. Otherwise, we prematurely open up the regulator and either potentially contaminate the system or at least get backflow into the inlet, which is not great. So our equation a little bit simpler. F1 equals F2 plus F3. We have some similar terms from a performance standpoint on a back pressure regulator. Lockup is still going to be the difference between a flowing and non-flowing condition. And your inlet pressure is going to decrease until you reseat. So similar to a relief valve, a proportional relief valve, as we increase the flow through the component, you're going to see the inlet pressure rise to try and keep up with it. So you're only able to get so much flow because you're only allowing that diaphragm off the seat so much, or in the higher pressure instances, the poppet's only disengaging from that seat so much. So the more flow you're able to get through there, the higher the inlet pressure has to be to achieve that flow. That's why you see all of these curves go up. So it's backwards from that. The lockup is going to be in the same condition, going from a zero flow to flowing condition. Like I started alluding to, accumulation is kind of the opposite of droop. Where droop, you see a pressure decrease as flow increases. Accumulation, you see pressure increase as flow increases. So same thing, it's just working backwards because you're thinking of the wrong, or the opposite condition. Instead of an outlet pressure, it's inlet pressure. You've got to have more inlet pressure to get more flow. Any questions on that? Lee, I'll get to the dome-loaded regulator in a little bit here. The major difference between a pressure relief valve and a back pressure regulator, from an operation standpoint, they are near identical. Real quick, if you look at how this is set up, you've got an inlet pressure going to a sensing element that opens and evacuates the system. If we look at a relief valve, here we go. If I go through my EDTR here, if I look at a relief valve and I look at the cutaway of this, you've got a spring-loaded poppet or sensing element that makes a seat. So when our inlet pressure exceeds this, you go to a vent. So from a design standpoint, it looks a little bit different. Operationally, it does the same thing. The big difference between them is the sensing element diameter. If you look at a relief valve, typically it's a real small diameter. There's not a lot of space there, which means that it's not as sensitive to changes in upstream pressure compared to the regulator that's got a very large diaphragm or piston that's able to sense smaller changes in system pressure. So it's going to be more sensitive to the actual cracking pressure that you want to have. And that's typically called out in a relief valve anyways, that you're usually within a couple PSI or a percentage. Just because of the size of the sensing element, it's less sensitive to changes. That's the big difference. Greg will be in touch about sending a presentation afterwards, but I appreciate it. Yes, we can get portions of this to you without an issue. So yeah, relief valve back pressure regulator, essentially doing the same thing. We have used back pressure regulators in a relief application because of the low pressure nature of it. Relief valves typically don't go very low. Ours are kind of limited to 10 psi. If you needed a relief pressure at 2 or 3, you can't use a relief valve. You've got to go to a back pressure regulator, something that's going to be more sensitive to your pressure changes. Good question. Thank you. Choke flow, this happens in a back pressure regulator as well. That's when it's full open. It's not regulating anymore. It is a restricting orifice. Whoops. And our optimal flow range is going to be referenced as the same. It's going to be where the flow curve is its flattest, as you're seeing it here. That's where you want this regulator to be used, in that flow at about that pressure. And I guess what I didn't talk about before, with a flow curve, if you have a range in here and it's not exactly where you want it to go, let's say you don't want this at 80 psi, you really want to know what it is at 70 psi. For most regulators, you're able to drop a flow curve down. You don't want to move them up because it may go outside of the regulator capabilities. You can take this curve and move it down to get a representative performance curve out of them, whether that's a back pressure regulator or pressure reducing regulator. If you see a published flow curve, you can move it down. Don't shift it left or right, but you can move the curve down to get a representative performance out of that regulator. Should have brought that up before. 2 more, creep. Creep exists. In this case, because it's a back pressure regulator and we're trying to control the inlet pressure, this is going to cause the inlet pressure to drop, assuming it's a closed volume and it's not being replenished by a compressor or something else. If it's a closed volume, creep is going to bleed that system over time until you get to 0, because it's relieving through that regulator, typically to atmosphere. And again, this is contamination in the system that's preventing the diaphragm or piston from closing onto the seat, or the poppet from closing on the seat. So filters, we want to use filters. And again, with the flow coefficient, it's measured when the regulator is fully open. So don't size based on flow coefficient, size by flow curves, or the flow curve generator. Make sure that it's capable of doing what you want. Don't use CV, it's misleading. So any questions on anything that we've covered so far? Okay. So, excuse me, there's been a couple of questions on dome-loaded regulators and other things. We're going to get into that in this section. So this is going to be regulator options and also some specialty regulator discussion. Because not every regulator is pressure reducing or back pressure. There are some other specialty regulator applications that we're going to get into. Real quick, when we talk about venting, a lot of the regulators that we've talked about already, there is no self-vent and there is no captured vent as a standard from Swagelok. That means that if you were to back this handle out, the downstream pressure does not vent out of the cap. So if you have a valve here that's off and your regulator is off, as you back this handle out trying to relieve this pressure, it won't do that. There's nowhere for that pressure to go. In order to get this pressure out, you've got to have another valve. And there's a vent hole in here that's really just to account for any change in volume in here, or if this diaphragm fails, gives us a place for that gas to escape or liquid to escape right under the handle. So no self-vent, no captured vent. Another option is a no self-vent and a captured vent. So instead of letting that gas or media escape under the handle, let's say it's a non-desirable system media, let's say it's chlorine or something that's pyrophoric. If there is a failure, you don't want that right by the technician. So we put a seal on the stem, on the actuation stem, and we thread the body cap here to allow you to put a fitting and redirect the gas or media elsewhere. So again, if there is a failure in the diaphragm or the piston, this has got to go someplace that allows you to safely redirect it to keep the technician and the facility safe. A self-vent regulator. Again, if we think of our valve down here that's off and our regulator that's off, if we needed to vent this volume out, we can back the handle out. In doing that, that exposes a hole in your sensing element that then exposes it to this body cap as well. So we could take that volume and dump it through here and depressurize the downstream side of the system. At this point, it's not captured, so it's going to come right out under the handle, which if you were to guess what the fourth one is, based on this sequence, I think I heard it. It's going to be a self-vent and a captured vent. So again, this is going to allow you to vent the downstream side and then capture that volume so it's not right by the technician. Most of the regulators that we have dealt with in the past have been this style. All three of these are options for most of the K-series regulators as options. So we've got a question here. What diaphragm should be chosen for reactive or corrosive gases? Our diaphragm material is one of two different materials. It's either an alloy X750, which is a high nickel alloy, an Inconel, or Hastelloy. Those are the two options that we have on our K-series diaphragms. The pistons, I believe, are always stainless steel, or we can get into some more exotics. I think you can get a piston in Hastelloy as well. When we get into the larger regulators, the RHPS series, they're all going to be an elastomer. So it's either going to be a Viton, a Buna, or an EPDM. It's going to be one of those three when we talk of really 1/2 inch to 4 inch. It goes to an elastomer diaphragm. So we want to choose one that's going to be appropriate and compatible with the system media. Our standard is X750. It's an Inconel nickel-based alloy. A quick overview of the K-series regulators that we have. We've got 9 pressure reducing regulators. We've got 5 back pressure regulators within the K-series. There's more in the RHPS series. And then we've got 3 specialty regulators. There's a gas cylinder changeover regulator, which we call a KCM. And then there's 2 vaporizing regulators. One is going to use steam, one's going to be electrically heated. I want to talk real quick about the KCM, the changeover regulator. The intention with this is to allow you to hook up 2 cylinders and allow continuous flow to your system. So it allows your primary supply, or supply 1, to bleed down until about when you would want to change it over. It could be 500 PSI, it could be 250 PSI. When it reaches that threshold, the regulator automatically switches over to your second supply. So you don't need to have a technician situated there, waiting for the cylinder to deplete. It's going to automatically change over from supply 1 to supply 2. So you're seeing 2 different versions of this. This one is kind of the standard offering. This one has a couple more bells and whistles, some isolation valves, a vent valve. There can be as many or as few additions to this. You can add hoses, you can have the CGA fittings, you can have purge ports. You can do a lot with these to configure them to what the system actually needs. So real quick, I've got a video of how this works. And then the other way. So in this case, both of these gas cylinders are pressurized. Right now we've selected the primary supply as the feed, and we're going to set an outlet pressure. And what you're going to see is this. After it reaches your changeover pressure, you're going to see the secondary supply starting to run. So right now we set an outlet pressure, the primary supply is starting to drop. There's no sound in this because it's just gas whistling through this tube, which for a couple of seconds is not enjoyable to the ears. So we're approaching this changeover pressure. And as you can see, this outlet pressure is not moving. So at this point, this cylinder stopped. We're now pulling from the second supply. This handle doesn't change. This handle changes when you want to go to the secondary supply. So in this case, now that we're running the secondary, we want to change this cylinder out. So we're going to switch that handle over to the secondary supply. So this is going to allow us to change out this primary and then switch it back to the primary while the system's running. And ideally, you want to have an isolation valve in here just to make sure that you're not counting on the regulator on its own to not open this up to the system. So we're pulling from the secondary supply right now, but we've just replaced our cylinders. We're going to kick that over, and now we're running the primary pressure instead of the secondary pressure. So again, the nice part about this, there's no interruption in gas flow. The flow is going to stay exactly where it is because you're doing a two-stage pressure reduction, so your supply pressure effect is taken into account with this, especially in this case where you're running such a small volume. We're not seeing an interruption in gas supply and going from a primary. Now we're pulling from the secondary pressure. Any questions on that? As we talked about the Joule-Thompson effects, one of the best ways to combat that is to use heaters to heat the gas before it goes through, to make sure that when you do have that significant pressure drop, we're not frosting up on the outside here. So Swagelok has two different ways. You can either steam heat it or you can electrically heat it. The intention with this is to heat the gas before the pressure drop. So your inlet comes in, hits the steam, which is not exposed to the system. It's kind of encapsulated in this tube as it runs through there. So your system media goes around this steam heated piece of tubing. And at that point, you have a pressure reduction that goes to the outlet. The same thing happens on your electrically heated, except there's no steam. You're sending current through a heating element. You're preheating the gas before the pressure drop and so that it can go to the outlet. So there's two options that we can do with a regulator. Sometimes the flows that you need to get through there are larger than what these can accommodate, but we do have these as options from either a steam heating or an electric heating. We can help size those as well, because sometimes they can be a little finicky. We're at about 12 o'clock now. If people have to drop off, thank you for your attendance. If you have time to stick around, we've got a couple more slides, but don't feel bad if you got to run. The RHPS, I want to touch on this because this is where the dome loading happens. The K series does not have a dome loading option. They are all spring loaded. The RHPS introduces dome loading as a means to control the outlet pressure. We also have some different end connection options. It's not just threaded. You can have industrial flange or straight thread end connections on there as well, or weld ends on some of them. So this is the offering of the regulator line. You're going to see traditional spring-loaded pressure-reducing regulators. You're going to see traditional spring-loaded back pressure regulators. We've color-coded the handles, red for pressure-reducing, blue for back pressure. Then we have dome-loaded regulator options for both pressure-reducing and back pressure. And then there's some specialty regulators beyond that that we are not going to address in this session. But if you have interest, I can certainly walk you through those when the time comes. To get an idea of size, this is a 3/4 inch pressure regulator. This is a 4-inch dome loaded with a pilot with an external feedback line with giant flanges welded on the end. Just to get an idea of some of the scope and flexibility that we have to modify a regulator for an application. This would be done at corporate, but we do have a way of creating this style of solution. This is a pretty niche application. But it can be done. We can weld this giant inlet to create the flow that we need through here to the outlet. And this is a low pressure application. I believe the outlet pressure is 10 PSI, but because of the flow, we need to size up the end connections to these enormous connections. So when we looked at the flow curves earlier, you see a varying intensities of droop. Ultimately, what we're trying to do when we're sizing regulators is to flatten the flow curve. and go from, you know, the baseline to a good, better, best scenario. And there's a couple ways to do that. One of the easiest ways is to change your loading mechanism, to go from a spring to a dome-loaded regulator. When we do that, we take out this mechanical spring and we replace it with a pneumatic force, which means that the cap has to be ported to allow a gas to go in there. But you're going to be doing the same thing. It's still going to be applying a pressure to the top side of your sensing element, which is going to push the poppet off the seat to allow flow through there. But because of the nature of a spring compared to a gas, the spring is going to be more sensitive to changes, and it's going to cause more oscillation back and forth than the gas. Well, the gas is going to allow that outlet pressure to stay steadier with changes to your system conditions here. This is typically how it's run. So you're going to notice there's no cap up here to adjust the set pressure. You've got to run a pilot regulator. In this case, it's using the same process gas as your pilot gas. You're going to create a pressure drop to create a set point on the top of the dome-loaded regulator, and then you're going to have a dynamic bleed from there back into the system, because we don't want to run a regulator in a no-flow condition like we were showing earlier. You want it to run through there, even if it's the smallest amount. We don't want to capture it in here. We want it to run from the dome back into the system. So that's one way to do it. If you don't like that idea, oh, sorry, jumped ahead. This is what that dome-loaded regulator looks in a kind of compact offering from Swagelok. So the inlet and the pilot, all of this will come to you ready to go. So it's pre-plumbed. We've got an orifice in here, but your inlet connection, your inlet gas goes in through a pilot regulator to the dome, out of the dome into the outlet. So it's self-contained, it's relatively small, but this is going to be a better way, or a better way to flatten the flow curve here. So like I was saying before, if you don't want to run your process gas, if you don't feel like running a natural gas or hydrogen or whatever your process is that you don't want to dome load, you can use an external source. You just have to bleed to something else. You don't want to run this into the system because then you're blending. But this is another way to do the same thing, is using an external pressure source to pressurize the dome to control the system. So this is a cutaway again of how it all works. Red is going to be your high pressure, and this purple color is going to be your low pressure. And in theory, all of this is going to be the same pressure from the dome to this line that reintroduces it back into the system, and the outlet should all be the same pressure within reason. So there's another way to flatten the flow curve. That's using external feedback. So instead of just having this dynamic purge, we're actually going to take some of this downstream pressure and run it back to the dome regulator itself. So it's going to go between this little stop plate and your sensing element, and that's going to make some changes based on what you want the pressure to be. When we set up regulator outlet pressure, ultimately that outlet pressure is right at that outlet connection. It's not taking into account any flow loss or pressure loss a couple pipe diameters downstream, and that's ultimately where you want that pressure. So we set it to 100 psi here. Down here we're at 95. This line is going to send that pressure signal back here saying, hey, we need more pressure. Open this up some more to get a more representative pressure down here. So we're adding another force to our balance of equation. The other way is, instead of going back to the regulator itself, you go back to the pilot regulator. So we're seeing another little wedge in here that's going to take that output signal, and instead of going to that, you're going back to the pilot regulator. So now you're making the change on this part, so this is going to be more sensitive and a even better performance than going directly to the regulator. So when we talk good, better, best, this is between better and best. Again, the same idea. We want to correct the signal in here so that it's representative down here, what we want. And this in practice is what that looks like. So it's a larger size than most are going to use, but your inlet comes to here. Pilot regulator drops the pressure to the dome, re-enters on the outlet side. We still have the outlet pressure running through there, and then we're going to correct it with this external feedback line to the pilot. And we have a gauge down here to make sure that the pressure that we want is the pressure that we get. There was one more. The best would be using an electronic regulator. So instead of counting on a spring, it's actually controlled electronically. So it's like a solenoid valve almost. Proportionaire makes a couple of good ones. To take an external gas supply to run to the top of a dome, and that's going to then take a transducer signal to adjust it. So instead of controlling it pneumatically, it's going to control it electronically. Would be the best. We don't get into those too much, but that's certainly an option as well. When we start looking at how flat that flow curve needs to be, you can get it pretty flat. So when I look at selecting a regulator, this I believe is one of the last slides. If you have a regulator application, the first thing I'm going to ask is what you want it to do. Is it a pressure reducing? Is it a back pressure? Or is it something else? What's the inlet pressure? And ultimately, I want to know what the range is. Is it a cylinder? Is it a compressor that surges? What's the control range? You know, the outlet pressure that you're desiring, but also what it can tolerate. That's going to determine what style of regulator it's going to be. Is it a diaphragm or a piston sensing regulator? Flow requirement is the big one. That's usually the piece of information that we're lacking. What is the demand? Because that's going to determine how big of the regulator it needs to be. What calculations I need to do, what calculations I can help you with to make sure that we're sizing a regulator that's appropriate. And then we look at system compatibility and functionality and the end connections. What does the rest of the system look like? What's downstream? Is there flow controllers? Is it going to a supply manifold or a distribution manifold that you can have a variety of flows going at the same time? It's important for me to help you by knowing what the rest of the system does, to know how the effects of those changes are going to affect what the regulator is able to do. And last is how it's got to be connected to the system, what size, what end connections, how it gets mounted. When you look at that 4-inch regulator that's 200 pounds, there has to be some consideration to mount it someplace. You can't just count on a bracket to do that. So it's important to know where it's going to go, who's going to use it, and how ultimately they need to be able to get to it. So when you need help and you get me on the phone and say, Derrick, I need help with this regulator, these are the questions that I'm going to be asking, just that you're prepared to make sure that what we're doing is appropriate. Again, this is my contact information, my email, phone number. More often than not, I'm available. I can also be on site when we get back to that state of being able to see people in person. I'm happy to look at a system in person or talk over the phone or virtually. So certainly keep your sales guys involved, but I'm here also as your regulator expert to help size and make sure everything works appropriately. Are there any questions about anything that we covered or anything that we didn't cover that you would like me to address? If you have questions that come up in the future, please let us know. But at this point, thank you for your time. Thank you for your attendance, and enjoy the rest of your day. Thank you.